Okay, let's just get right into it. We're about to take a look at one of the most fundamental facts in all of physics, a number you probably think we've got completely locked down. But what if I told you that we've never actually measured it? Not in the way you think, anyway. Here it is, the speed of light in a vacuum, what physicists call c. And look at that number. It's exact. There are no decimals, no rounding, nothing. This isn't just a measurement, it's considered a fundamental constant of our universe. And right here, right at the start, is the twist. The answer to that question is, believe it or not, no. We have never, not once, managed to measure the speed of light going in just one direction. And get this, we're so confident in that number that we flipped things around. We don't use a meter stick to measure the speed of light. We actually use the speed of light to define what a meter is. A meter is officially just the distance light zips through in a tiny, tiny fraction of a second. So how can a number be so important that we base our measurements on it, yet be fundamentally unmeasured itself? Let's break it down. The whole entire issue, this huge cosmic mystery, really just boils down to one single, surprisingly difficult problem. How in the world do you get two different clocks to be perfectly in sync when they're far apart? I mean, for normal stuff, this is a piece of cake. If you want to measure the speed of a baseball, you just need to know the distance it traveled and the time it took, right? Distance divided by time. Easy. But when you try to apply that same simple logic to light, you walk right into a massive logical trap. To measure the one-way speed of light, you'd set up a clock where you start the timer and a second clock at the finish line to stop it. Simple enough. But here is the absolute crux of the problem. Those two clocks have to be perfectly, absolutely, down to the nanosecond synchronized. And that's where the whole thing just completely falls apart. Now you're probably thinking, just sync them. What's the big deal? Well, let's try. Method 1, you could put the two clocks right next to each other, sync them up, and then carry one over to the finish line. The problem? Einstein's special relativity tells us that a moving clock actually ticks a little bit slower. So by the time it gets there, it's already out of sync. Okay, so what about method 2? You could just send a signal, a light pulse, from the first clock to start the second clock. But wait, the signal you're using to sync the clocks travels at the speed of light, which is the very thing you're trying to measure in the first place. You can't use the speed of light to measure the speed of light. You see? It's a perfect, inescapable circle. You can't figure out one without already knowing the other. And this isn't a problem with our technology. It's not like we just need better clocks. It's a fundamental limit of logic and physics itself. So if we can't measure the one-way speed, how do we have that super precise number at all? Well, scientists came up with a very, very clever workaround a long time ago. The solution is actually beautiful in its simplicity. If you can't trust two clocks, just use one. What you do is fire a pulse of light at a distant mirror, let it bounce back, and then you time the entire round-trip journey using the same clock for both the start and the finish. This gives you the two-way, or round-trip, speed of light. And essentially, all of our measurements are based on this method. And hey, this isn't some newfangled problem we just discovered. The very first successful measurement of the speed of light here on Earth was done by a physicist named Fizeau way back in 1849. He used this crazy setup with a spinning cogwheel and a mirror 8 kilometers away. But what was he measuring? You guessed it, the round-trip speed. Now this is where the story takes a turn from a cool physics problem to something truly mind-bending. Because it turns out the person who understood this synchronization problem best was none other than Albert Einstein himself. Just think about this for a second. Our round-trip measurement always gives us an average speed. But what if the journey isn't symmetrical? What if light travels at, say, half its normal speed on the way to the mirror, but travels instantaneously on the way back? The average speed for the whole round trip would still come out to exactly c. We would have absolutely no way of knowing. In his groundbreaking 1905 paper on special relativity, Einstein addressed this problem head-on. He basically said that we have to assume, and get this, we establish by definition that the speed is the same in both directions. It wasn't something he proved. It was a premise, a starting point he needed to make the rest of the math work. He even doubled down on this later, making it crystal clear. He said this choice is, and I'm quoting, neither a supposition nor a hypothesis about the physical nature of light, but a stipulation that I can make of my own free will. It's a convention, a choice that we've all agreed on, not an experimentally verified fact. And this foundational assumption actually has a name. It's called the Einstein Synchronization Convention. It's the agreement that we're all going to define our clocks and our physics as if light travels at the same speed in all directions. Why? Because it's the simplest and most elegant solution. But we have to remember, it's still a convention.
So what would reality even look like if this convention were wrong? What if the universe was actually lopsided and the speed of light really did depend on which direction it was going? Well, the consequences get pretty strange pretty fast.
Let's run a quick thought experiment. Say you're sending a message to an astronaut on Mars. The signal goes there, and a reply comes back. The whole round trip takes 20 minutes. Using our standard Einstein convention, we just naturally assume, okay, 10 minutes to get there, 10 minutes to get back. But what if reality is lopsided? What if the message actually took the full 20 minutes to reach Mars, and the reply came back instantaneously? From our point of view here on Earth, the experience is identical. We send a message at 12, we get a reply at 12:20. There is no experiment we could do to tell the difference. This creates a huge paradox for the astronaut on Mars, though. So if the signal we sent at 12 o'clock takes 20 minutes to arrive, it's 12:20 on Earth's clock when they get it. But the astronaut, using the convention, assumes it only took 10 minutes. So what do? They set their clock to 12:10. The crazy result is that the clocks on Earth and Mars are now permanently out of sync by 10 minutes, and no one could ever know. And this leads to a truly bizarre conclusion. If light from Mars back to Earth were instantaneous, when we look up at Mars through a telescope, we wouldn't be seeing Mars as it was minutes ago. We would be seeing it in real time, exactly as it is right now. But that astronaut on Mars, looking back at us, they would still be seeing Earth as it was 20 minutes in the past. It's just wild to think about. So while this might feel like just a philosophical game, it really points to a profound mystery about how we measure reality. And it exposes some of the fundamental limits of our own knowledge. You might be wondering, okay, so what? Why does this matter? And for most physicists doing their day-to-day work, it doesn't really. They accept the convention because it's simpler, Occam's razor, and all the physics built on it works perfectly. But other thinkers argue that it is absolutely vital to remember that this is an assumption, not a proven fact. It reminds us that something as basic as two things happening at the same time in different places, well, that's really more of a human definition than a physical reality. And that leaves us with a fascinating, kind of unsettling final question. If we can't ever truly know what time it is now on another planet, what does now even mean across the vastness of space? And it forces us to wonder, what other pillars of our scientific understanding are not hard-won measurements, but are simply elegant, useful conventions we chose to build our reality upon?